thank you for attending. I'm Jan Michalevsky from CryptoSat, and I'm going to explain how we're building the trust infrastructure for Web3 in space and what it means. So just a little bit about who we are, the company. CryptoSat is a combination of space and cryptography. My co-founder is Jonathan Weintraub. He brings a lot of aerospace expertise, and I'll go into some of the things he did previously. Also worked in his career on Waymo's autonomous vehicle, launched a bunch of things into space. Some of our advisors you're probably familiar with, Dan Bonnet, Juan Bennett from the Protocol Labs ecosystem, Ben Fish from Espresso. So, and myself, my background is in cryptography and security. Just to elaborate a bit on the kind of space aspect and the background, some of the background of that led us to do what we're building nowadays at CryptoSat. So, my co-founder Jonathan previously launched an actual spaceship that crash landed on the moon in 2020. Crashing a party, you're still having a good time, and that was the first time a privately owned and operated mission was conducted that wasn't government driven. The other thing we're showing here is a model for trying out agriculture in space, growing chickpeas aboard the International Space Station. So that's another one of his achievements. So basically, taking all of this expertise and combining it with security and Web3 and crypto, we're essentially came to building the trust infrastructure for Web3 in space. And what we do for that is actually building trusted execution environments that are launched to low Earth orbits because, and as you can imagine, satellites are not very easily physically accessible. When I'm saying not very easily accessible, they're actually really not accessible. It's pretty much science fiction today to successfully dock to a satellite and do anything to it. Those are some of our, so those are two of our launches. We launched Crypto 1 in May 22, and Crypto 2, our second crypto satellite, earlier this year in January. And this is actual footage from Florida, from Cape Canaveral. We're watching the launch. Just to tell a bit more about the satellites themselves. So what we're building is small satellites. It's something like that, that are launched into relatively low Earth orbit. That's where most satellites nowadays are going. If you're thinking about something like Starlinks or other satellites like Project Kuiper by Amazon. So those are going into those low Earth orbits. It's pretty affordable launches compared to geostationary, and by keeping this small form factor, we're able to do it at a pretty affordable cost, which enables us to basically keep launching more and more of the satellites instead of working for a prolonged period of time on one satellite. And that enables us to take advantage of technology advancements in the space industry. So each one of those, what's called CubeSats, is basically a stack of boards. One of them is what we call the mission computer that kind of can control the orientation of the satellite, different low-level functions, powering different boards. And we have what we call the crypto cards, which perform the actual cryptographic logic. In addition to that, we also have access to a ground station network through which we can communicate with our satellites. That's a third-party network. And we build a convenient API, basically REST APIs, which is kind of unique in the space, basically being able to access REST APIs and transmit commands and get responses from the satellites directly. You can go to this website to see the position of our satellites and where they're currently at. And something cute we built for developer onboarding and showcasing how to work with the CryptoSat satellites and the APIs is what we call CryptoSim, which is a sandbox simulator. And it combines kind of an interactive tutorial with explanations about the APIs and a sandbox where you can try some of those APIs out. For yourself and get accustomed to how you work with the satellite, with asynchronicity, with delayed responses, and so forth. So that's something that you can actually see on setbox.cryptosat.io. Some of our milestones. So even prior to launching the satellites, we conducted experiments on the International Space Station to see how it is to operate in space and combine different cryptographic applications and Web3 applications with space operations. So for instance, early in 2022, we basically launched a multi-sig wallet onto the International Space Station and conducted an experiment along with Zengo. We later launched our first satellite and then did another experiment on the ISS, where we conducted a trusted setup for a ZK SNARK scheme used for private voting by one DAO. That followed by the launch of our second satellite, which was instrumental to contributing to the KZG ceremony run by Ethereum. So that's actually an interesting part to spend a minute on. One of the use cases for such a secure execution environment that's completely physically isolated and is very transparent in terms of its security model makes it very easy to explain why nobody can tamper with this compute environment, is trusted setups, trusted cryptographic setups. So one instance of that was participating in this ceremony for creating the trusted parameters for the KZG polynomial commitments that were required for danksharding, which is part of the move of Ethereum to its next version to lower transaction costs, increase transaction throughput. So the KZG ceremony was decentralized. It basically consisted of many parties contributing cryptographic parameters such that if one party is not compromised, that's enough to guarantee the security of the ceremony. But as part of that, the Ethereum Foundation also wanted to create a very clear story around certain contributions that are unique in terms of the source of randomness and in terms of security. And that was one of the special contribution phase participants. So we generated those cryptographic parameters in space, signed them, delivered them to the Ethereum Foundation, and then users could independently verify using the CryptoSat public key that it actually came from a CryptoSat satellite. So that's just an example of how this kind of an environment can be used for cryptographic setups. Later on, we did some work on co-signing transactions from space, again with a wallet company called Defense. So that resulted in a successful proof of concept of participating in an MPC scheme. And now we're working towards the launch of our third satellite. So that's basically, now I want to go over a few scenarios, a few different use cases supported by CryptoSat, use cases that we already explored with different partners. And as I mentioned, one of the settings is trusted setups for ZK SNARKs. Not all of the SNARKs, not all of them need trusted setups, but some of the efficient ones can require that. For instance, Growth 16 is a good scheme across multiple parameters in terms of verification performance, proof generation, and so forth, and it requires a trusted setup. So essentially, in this setting, it's pretty simple conceptually. You submit a circuit, you submit the program over which you want to produce proofs to CryptoSat, to a CryptoSat satellite, and it generates the structured reference string and transmits it back. And it signs those parameters such that they can be delivered back to users, verifiers. They can even be put on a blockchain and verified by a smart contract independently using a CryptoSat public key that enables you to make sure that the response is actually coming from CryptoSat. So that's a very interesting application that kind of opens the door for potentially more frequent trusted setups and more frequent deployment of ZK snarks, because this ceremony, the bootstrapping of those schemes, is one of the kind of the more painful points. The other use case is securing wallets and transaction consigning from space. So basically, in this setting, we want to further improve the security of MPC schemes and guarantee that transactions cannot be forged by a very powerful attacker that can take over ground infrastructure. So basically, in the scheme, CryptoSat participates as another participant in the MPC protocol, in a threshold signature scheme as another signer, and it has a couple of advantages. So you cannot extract the key from the satellite, and therefore, as an attacker, you cannot sign transactions on behalf of the user just outside the protocol and outside their legitimate APIs. You may compromise the ground infrastructure, and that might enable you to request a signature or a signature share from one of the satellites. But there are still pretty important advantages going through this API, and that's auditing and basically creating an audit trail and application of different policies. So for instance, for some high-value transactions, you might choose to delay the transaction execution a little bit while giving a notification to the user that this transaction is taking place. And that enables you to respond if you notice some malicious behavior. And you also create a signed audit trail of all the transactions that are going through the CryptoSat API, which cannot be bypassed. If you could just steal the sign-in key, you could potentially just forge this transaction without leaving any trace and covering your tracks. So that's not something that's possible in this setting. So as I mentioned, we did this with Defense, which is an institutional wallet company. We're looking to expand this capability to additional partners and wallets to basically provide this security benefit. The last application I want to mention as part of this talk, and there are more applications, but that's an interesting one that we deployed across some blockchains, is the CryptoSat VRF Oracle. So the need for VRFs is well established. There are many different applications, including kind of nitty-gritty details of different protocols to more direct applications, such as on-chain lotteries. In this setting, basically, what we provide is a very reliable source of entropy, the problem we usually have with entropy is not that there's no good entropy around, like we can extract good entropy. The problem is with proving that you actually used good entropy and didn't just bias something in your favor, right? So that's where basically a trusted execution environment like that's very secure, tamper-proof, where it's very easy to explain the threat model, is useful. So we're basically generating the randomness in space. We're collecting entropy from multiple sources, both from standard random number generators and also from cosmic radiation. That's another useful source of entropy. We're assigning this random beacon, delivering it to the ground, and then we can deliver it directly to blockchains or expose via APIs. So on a blockchain, this could be directly, the source of the entropy could be directly verified by users. In this context, we would actually love to continue this effort and build an integration with Chainlink, where we could be a data provider as part of Chainlink's integration to many different chains. So we would love to see that happening, and we'll probably work on that down the road. So, sorry, move to the previous slide. So wanted to finish here and leave some time for questions if there are any. And welcome to get more details. Check out our documentation on the website. Join the Telegram group for more questions. Yeah, thank you very much.